All right, everyone, Mr. Graham here. Today I want to continue our discussion, or right now I want to continue our discussion of doing the derivative or differentiating functions. Before we get to the shortcuts though, there's some rules that we have to know. And just understand that these rules, you don't need to know them to do derivatives. You can always use the difference quotient to compute a derivative. These rules are just going to make the process a little easier. Using these rules does the same thing as when you use the actual definition of the derivative, the limit definition. So let's say that I have a function y equals 17x squared. So if I have the function y equals 17 times x squared and I want to find the derivative, and here I'm going to use this notation just to kind of get you used to seeing different notations. The derivative of this function with respect to x, the constant multiple rule says that I can take the constant multiple. Realize that by constant multiple, in this case, I mean the 17. 17 is a constant. It is always 17. There's no instant in time where 17 is not 17. So it is a constant and it is a multiple of my variable x, which in this case is squared. So what the constant multiple rule says is that I can do the derivative by just pulling the 17 out in front and then differentiating my x squared. And again, this is a different notation. This is the derivative with respect to x of x squared. So I could say, another way of writing this is that the derivative with respect to x of my function, which is 17x squared, is the same as just bringing my 17 out in front and then doing the derivative of x squared. And then until we know the power rule, we would just then differentiate the x squared using the limit definition and multiply our result by 17. Okay. Now the sum and difference rule says that if I have a function, say y equals 2x squared minus 3x, well then the derivative here, the derivative with respect to x of this function, so this is a way to notate that, then that's just going to be the derivative of each individual term. The sum and difference rule means that if I have a sum or difference, a plus or a minus between the terms, then I can just differentiate or do the derivative of each term in there individually and then just put them together and keep the appropriate symbol. So in this case, if I did this derivative, it would be the same as the derivative with respect to x of my function 2x squared minus, that minus goes here, the derivative with respect to x of 3x. And then I could actually apply the constant multiple rule here and say that, well, this derivative with respect to x, and I here use the different notation, doesn't matter what notation you use, the derivative with respect to x of this function will be, well, this is a constant multiple, I can pull it out into the front. 2 times the derivative with respect to x of what's left, x squared, minus, and here the constant 3 can come out into the front, times the derivative with respect to x of just x. Okay? Be consistent there. Okay. So those are the constant multiple and the sum and difference rules. They're going to make your lives a little easier. If this still is confusing, that's okay. Let's do some examples and I'll introduce the power rule now. Just so you know, I don't know how to do video editing, so you're going to have to watch me erase up here until I actually figure that out, which probably won't be anytime soon. All right. Now the power rule, and let me get our formula sheet, because you do have some calculus rules on your AP Physics C formula sheet that weren't on your AP Physics 1 formula sheet. There are a lot of rules there. We're not going to get into them. In the beginning, we're just going to be doing derivatives of polynomial functions. And so on your formula sheet, the power rule, it doesn't tell you that it's the power rule, but that is the name of it. The power rule says that the derivative with respect to x of a general function x to the n power, where n can be any exponent, will be equal to n, that power comes out to the front, times x raised to the n minus 1 power. This should make a little bit of sense because when we differentiated a quadratic, we got a linear function, right? The 2 examples that we did where we did the derivatives of quadratics, we got lines. Well, if n is 2 for a quadratic, n minus 1, that's the exponent, puts the exponent of 1 on the x, which x to the 1 is just x, okay? So this is the power rule. When I combine the power rule, the constant multiple rule, and the sum and difference rule, it makes derivatives actually pretty easy. And I'm going to show you some examples. It might still seem pretty confusing, but let me show you how non-confusing this happens to be. And first, let's do an easy one. Let's say f of x equals x cubed. Okay, and I want to do the derivative here. So the derivative with respect to x of this function of x cubed, well, in this case, n equals 3, right? So I'm going to have the 3 come out into the front according to the power rule, and then I multiply that times x raised to the n minus 1 power, which is just going to be squared. Okay, so that's our derivative. So if f of x equals x cubed, f prime of x is going to be 3x squared. And again, that lets us calculate the slope of this function at any point. If I want to know the slope at f equals 1, then I just evaluate the derivative when x equals 1, and that's going to be 3 times 1 squared, or 3. So the slope of this line, remember this line curves, right? It's a curvy line, but at x equals 1, the slope of the tangent line to that curve will be 3. And if this was a position time graph, that would say that our velocity is 3 meters per second, if we're measuring in meters per second, okay? So hopefully that's not too bad. Let's do another example where we're actually use the constant multiple rule. So let's say f of x equals 3x cubed. All right, well, the constant multiple rule says that the derivative is going to be 3. I pull the constant out in front, and then I do the derivative with respect to x of just the x cubed. And then so the derivative here then would be 3, and then I apply the power rule to my x cubed, just like I did here. So I bring the 3 out in front, times x to the 3 minus 1 power, which is just 2. And then I just multiply these two together. The 3's I multiply together, so I get f prime of x is simply 9x squared. So there's the derivative of this function, this original function up here. Okay. So it's much easier to do when you use these rules. And what the gist of it is that the limit definition of the derivative allows you to compute any derivative as long as you got the algebra skill. These rules, shortly after they figured out what the derivative is, then they figured out that, well, these rules shorten the process, okay? And so this is much easier. If I was to do this derivative using the limit definition, I'd take up my whole board, or at least half the board here. But I can just do it in a couple steps when I know these rules. And let's do one last example where we use the constant multiple rule, the sum and difference rule, and the power rule all together. Let's say I have a more complicated polynomial like f of x equals 3x cubed plus 2x squared minus 17x plus 42. All right, well, the sum and difference rule says I just do the derivative of each individual term in my function separately. And then the constant multiple rule says I can bring the 3, the 2, the 17, and in fact the 42 out in front. We'll talk about the 42 at the end though. So my derivative here is going to be 3 times the derivative with respect to x of x cubed, which we should know how to do now, plus the constant multiple here, 2, times the derivative with respect to x of x squared, minus 17, that's the constant multiple, times the derivative with respect to x of just x, plus, now that 42, that's going to be 42 is the constant, times the derivative with respect to x. I'm running out of room here. I'm sorry, guys, I'm going to rewrite this. Again, I don't know how to edit videos, so you're going to have to bear with me. So this is going to be 3 times the derivative with respect to x of x cubed, plus 2 times the derivative with respect to x of x squared, minus 17 times the derivative with respect to x of x. And technically, this is x to the first power. X by itself is x to the first power. Plus 42, that's the constant, and then times the derivative with respect to x. I'm going to put an x there, but what's the exponent on that x? Well, this is 42 times x to the 0 power, right? So that'll be x to the 0 power. And then I just evaluate the derivative using the power rule for each term here. So my derivative is going to be the 3 times the derivative of x cubed. I just bring the 3 into the front, times x to the 3 minus 1. So that's going to be x squared. Plus 2 times, then I bring the 2 out in front. X squared, the derivative, I bring the 2 out in front, times x to the 2 minus 1. That's times x to the 1 power. Minus 17 times the derivative of x to the first. Well, I bring the 1 out in front. 1 times x to the 1 minus 1, which is 0, plus 42. Then I bring the 0 out in front, times 0 times x to the negative 1 power. 0 minus 1 is negative 1. Well, it doesn't matter that x is raised to the negative 1 because 42 is now multiplied by 0. And so that last term just goes away. And so finishing this off, I get that the derivative is equal to 9x squared plus 4x. I don't have to put the 1 there, it's implied. Minus 17, because again, x to the 0 is 1, and then plus 0. Because 42 times 0 times x to the negative 1 power is just 0, so we tend to leave this one off. And so that's our derivative. Pretty complicated one, but again, if you use the difference quotient for this, try using the difference quotient for a cubic, and it will be a nightmare of algebra. These rules make it so much easier. All right, so those are some examples of using both all the sum and difference rules, the product rule, and the constant multiple rule to do derivatives of more complicated functions. And realize that the reason we need to do this in physics is because now we can talk about non-constant accelerated motion, because we can do the derivative of any function, of any polynomial. It's not too bad as long as you know how to apply these rules. And that's about